One very common situation where you come up with inconsistent systems is if you're trying to find a line of best fit through some data points. So if you go out into the world and observe some phenomenon to collect some data that you suspect should be linear, so if you have a lot of data points, if you have theory that says they should be linear, usually they aren't actually going to line up perfectly. They might get close, but they aren't going to exactly be on the line just because of measurement error or other physical phenomenon. So what we'd like to do is, if we have some collection of data, we'd like to come up with some nice way, some sort of theoretically justified way of choosing a line, so finding a slope and y-intercept that somehow produces a line that best fits the data that we have. And one way to do this is, so if this is all taking place in some coordinate system where we have an x and y coordinate, one way to decide what we mean by the best fit is just to insist that for every x coordinate where you have a data point, right, measure the distance between the data point that you have and your line. That, right, we'll get this distance for each one of our data points. Add those distances together. Those distances should be as small as possible. So we will know we have the best fit line when this sum of distances is minimal. Actually, it's a little inconvenient to use the sum of these distances because it turns out distance doesn't behave very well because it's not a differentiable thing usually. So it's actually better to minimize, instead of minimizing the sum of distances, minimize the sum of the squares of the distances. So, if let's zoom in on one of these points. Okay, so this is one of our data points, so maybe it's x1, y1. And up here, right, what is this point? Well, this is whatever the line gives you at this x value. Well, here's the line, right? Y equals mx plus b. So the x coordinate here is x1 still, but the y coordinate is what the line says it should be, and that's m times x1 plus b. So the vertical distance between these points is just, because they have the same x coordinate, the distance between these points is just the difference in y coordinates. So that's mx1 plus b minus this y coordinate, so y1. But again, we're going to square instead of leaving that alone. One reason it's nice to square is because you have to worry about, well, which order do I subtract these things in? But if you're squaring it, it doesn't matter what order you subtract them in. So this is the vertical distance just for this single point. We need to add up the corresponding thing for all of the other points. So what we're going to do is, given these data points, we need to find the slope and the y-intercept that minimize this total squared error. Now, because this is squared, this doesn't really look like a problem in linear algebra. So we would like to use all of our linear algebra tools to solve this problem. So we need to somehow rephrase this in a way that makes it look like linear algebra. Well, the sum of squares is another way to, one way that a sum of squares shows up in linear algebra is as the square of a magnitude of a vector. But what vectors? I mean, right, the square magnitude of a vector, right, the entries of the vectors would show up here. So what vector is it here that we're finding the square magnitude of? Well, it looks like there's two, right? There's this one, mx1 plus b, all the way to mxn plus b. So that would be, right, mx1 plus b down to mxn plus b. And then there's the one with all the y's, so minus this vector with all the y's, y1 down to yn. So this total error thing that we're trying to minimize is actually the square magnitude of this vector. But another way to rephrase this, right, so this vector here, mx1 plus b down to mxn plus b, there's actually a nice way to rewrite that. This is actually the matrix x1, 1 down to xn, 1 times mb. Okay, like so. So what we're trying to do is find the vector mb so that this product, x1, 1 down to xn, 1 times mb is as close as possible to y1 down through yn. But this is exactly the situation that we can solve with our normal equation, right? So really what we're asking for, translating this all into linear equation language, what we're looking for is a least square solution to this equation, x1, y1 down to xn, x1, 1 down to xn, 1 times mb equals y1 down to yn. Okay? We expect this system to be inconsistent because it has more rows than columns, unless you have only 2 data points. So if this is inconsistent, what we want is a choice for m and b that will make the distance between this vector and this vector as small as possible. But the distance between these two vectors is exactly this error expression that we came up with up here. Well, again, this is exactly what the least squares idea gives to us. So what we can do is solve the associated normal equation. So to find the line of best fit, right, for this data point, we need a least squares solution for this system of equations. And so what we'll do is just solve the associated normal equation. So that's this guy here. Right here is A transpose A times our vector equals A transpose times our right-hand side vector. All right, so let's see how this works with an actual example. So here's a line, here's some data points. Let's find the line of best fit. Now, I'm not going to do all the calculations by hand, just because it's not very interesting to watch. So instead, let's use Sage. So somewhere around here, I have Sage. There we go. Okay, so this matrix M that I have set up is just a matrix with all the data points. So if I ask Sage to plot these data points, right, here are the data points. All right, you can see that the line of best fit ought to sort of go up and to the right somehow, but what exactly should its slope and y-intercept be? So what we'll do is, first we need to build our matrix A, and that's what these two lines do. So I'm making a copy of the matrix M. I'm replacing its second column with all ones. So if we go back here, right, this matrix A is just this. So in Sage, how I have it set up is M is x1, y1 down to x and yn. So what I've done to get this matrix A is I've just replaced this second column with all ones. All right. And so here's that matrix A, right? The first column is just the x values from our data points. The second column is just all ones. So next thing we need to do is make the normal equation. So to make the left-hand side matrix for our normal equation, that's A transpose A. So I'm taking this A matrix and I'm multiplying it by its transpose. That gives me the left-hand side matrix for our normal equation. The vector on the right-hand side of our normal equation is just the y values. That's what this here is. It's the second column of M, which is just all of the y values. So we're taking the second column of our data points, which is the y values, and multiplying by the transpose of a. So that's the right-hand side for our normal equation. And then we can just ask Sage to solve this system. So it has a fancy way of doing that, of solving this kind of linear system. You take your matrix for your left-hand side, you call this method solve right, and then you give it the vector on the right-hand side. And that gives us a solution, which is these messy numbers right here. Let me comment this one out. So these messy numbers here, the first one is the slope, and the second one is the y-intercept of the best fit line. So what we can do now is ask Sage to plot the points that we started with together with, so here I'm plotting the best fit line itself. So right, the first component of, or the first entry in V is the slope, so slope times x plus the second component is the y-intercept, so this is just slope times x plus y-intercept, and I'm going to plot this line for x values from 0 to 10. All right, so you can see those are the same data points as before, and this line that we've produced using this least squared ideas is a best fit line. Right? It's hard to know just by looking if it genuinely is, but it certainly looks plausible. And assuming we did all the math correct, then this line is the only line that minimizes the squared distance, the squared vertical distance between the points and the line.